All right, so two more periodic trends that we're going to go over in this video are electron affinity and electronegativity. These are a little bit related. Electron affinity is the energy change associated with adding an electron to a gaseous atom. How much energy is usually going to be released in that process. So you have some element X in the gaseous phase, you're adding an electron, and how much does it make to make that anion? So it's sort of the reverse process of ionization energy. And so here are the values. Um, you can see that as you move on the right on the periodic table, the halogens, right, fluorine, chlorine, bromine, iodine, astatine, all have very high electron affinities. They want to get that one extra electron to become like the noble gas configurations. And if you're far on the left of the periodic table or noble gas, you're going to have an electron affinity very close to zero. So radon is an example, noble gas, basically very low electron affinity. Chlorine, very high, halogen, some of the transition metals, if they have a particularly stable configuration, they could be fairly low as well. Like manganese has a half-filled shell, which has some stability associated with it. A much more useful metric, in my opinion, is electronegativity. And electronegativity really, we talk about it for individual elements, but it's always in relationship with how elements join up in compounds. So it's the ability to attract electrons to an element itself within a compound. And the trend is that electronegativity increases across the periodic table and decreases going down the periodic table. And this has to do with the effective nuclear charge and the distance of the electron from the nucleus, sort of like before. So the top right corner of the periodic table, excluding the noble gases, has the has the elements with the highest electronegativity. So nitrogen, oxygen, fluorine, chlorine. Sometimes these are called the gang of four. They really want to have filled orbitals. They want to have noble gas configurations. And so the best way for them to do this is to gain electrons. And so they are the most electronegative elements. Fluorine is the most electronegative element. So here are the values. There's several different electronegativity scales that your book goes over. You don't really have to be concerned with the differences between the scales. They're all pretty similar. The common one is the Pauling scale, which is found here, named after Linus Pauling. You can see fluorine at the top right has an electronegativity of 4, and francium has an electronegativity of 0.7. Cesium and francium. Francium is very radioactive. There's only a few elements that you can make at any single time. So really practically, we're talking about cesium. So cesium is the most electropositive or least electronegative element at 0.7. So that really is going to give up electrons, cesium is, and then fluorine is the most. But you can see going down the period, from lithium to cesium, it's decreasing. From fluorine to astatine, it's decreasing. And going across any row here, it's more or less increasing. There are some bouncing rounds that happen. Manganese, again, is kind of an exception where it goes down because of the half-filled shell. So Linus Pauling did this. Linus Pauling is definitely an interesting person. He won the Nobel Peace Prize and the Nobel Prize in Chemistry, which is a pretty interesting combination. The Peace Prize was for non-nuclear proliferation. So he's a big player in the Cold War, trying to help countries be more peaceful to one another. That's pretty important. And a lot of the stuff that he did had to do with bonding in terms of chemistry. And so he devised this idea of electronegativity. And how he defined it was, if you have an element HX, okay, if things are, if electrons are, that covalent bond is being shared equally between H and your other element X, you would expect that the HH bond energy in a hydrogen atom and the XX bond energy, that the average of those two energies should be the bond energy of HX, okay? But if there's a difference between that, that's actually reflective of electronegativity, okay? And so that's how this was computed by him. Very, very actually simple idea. And then it's just scaled to be some fairly nice numbers.